All right, so we're going to talk about NMR spectroscopy now. So throughout the semester, we've been doing reactions to make molecules on paper, but how do you know what you have made actually in the lab? And the way you know what you've made is spectroscopy, and most commonly, NMR spectroscopy. So NMR spectroscopy is the way that we're able to identify the carbon-hydrogen framework of a molecule and figure out its structure. Um, this is kind of the most regularly used method to determine the structure of an organic compound. It's basically the first thing you would do after you make any compound in the lab is you would go take an NMR. So the picture here is actually our NMR. And what you see is basically just a great big giant thermos because an NMR has a superconducting magnet in the middle of it. And superconductors are only superconducting at really low temperatures. And the magnets in NMRs are only superconducting at liquid helium temperatures. So this whole big beige thing that you see is basically just a thermos. There's an inner thermos or an inner dewar that holds liquid helium to keep the magnet cold, and then there's an outer dewar that holds liquid nitrogen to keep the helium cold. Um, and liquid nitrogen is significantly cheaper than liquid helium, so you use that to try to keep the liquid helium cold so that you don't have to replace it very often. So we've got a magnet. And so why do we have a magnet? So we're going to talk about kind of the basics of how an NMR works. And so we're going to put on my physics hat for a bit. And so nuclei all have a spin and a charge. So uh, spin on an atomic level or subatomic level is quantized. There are only certain allowed spins um, that can happen. And so nuclei with plus half or minus half spins are observed with the NMR. So that gives us 1H, the carbon-13 isotope. So most carbon is carbon-12, but the carbon-13 isotope can be seen in the NMR. Fluorine-19 and phosphorus-31. So if you remember some physics, um, a spin plus a charge produces a magnetic field. So every single hydrogen in your molecule is an itty bitty teeny tiny magnet. And so the NMR has a strong magnetic field, and we use the magnetic field of the hydrogens combined with the magnetic field of the NMR to help determine the structure. So I'll have this slide up, but we're going to kind of cut to some drawing. So when you have the NMR, you're going to have a big magnetic field from the NMR that you put your sample into, and we're going to call that B. Yes, for some reason they decided that B would be the symbol for magnetic field. I don't know, blame a physicist. And there are two possible kind of ways that your hydrogen and its magnetic field can arrange itself. So you could have your hydrogen, you could have your hydrogen lined up with that magnetic field. And this is called the alpha state, and it is low energy. Or you could have your hydrogen lined up with its magnetic field against the magnetic field of the NMR, and that is the beta state, and this is high energy. So when you put your sample into the NMR, all the little magnetic fields on all of your hydrogens will align with the magnetic field of the NMR, and they will all exist in the alpha state because that is low energy. So you drop your sample in, you have your magnetic field from the NMR, and then you have all the magnetic fields from all of your hydrogens all line up together and point in the same direction. So this is kind of like when you have two like magnets and they have a north and a south, right? If you push the north pole and south pole of two magnets together, they go together because those fields are pointing in the same direction, right? If you take the two north ends of a magnet and try to push them together, they repel each other because those magnetic fields are both pointing at each other. So they're pointing in opposite directions. And so they don't go together. That's high energy. So you want to be in the alpha state. So to actually get a spectra, we're going to go back here. Here's our B from our NMR. And so we have a hydrogen chilling out in the alpha state. And then what will happen is we use radio waves to give these hydrogens energy so that they go from the alpha state up in energy. They get excited to that beta state, right? So now they're in the beta state. And they don't want to stay excited in this high energy beta state. So what happens eventually is they relax and that hydrogen goes back to the alpha state. And when that happens, when you relax down, there's energy that's given off. That is almost a word. Let's try that again. There's energy that is released. So what the NMR is actually observing is it is observing the energy released when the hydrogen goes from the beta state, the excited beta state, and relaxes back down to the alpha. So the NMR sees this energy released and observes that, and then that energy is used to generate signals in the NMR. And so the difference in energy between the beta state and the alpha state tells us about the environment that the hydrogen that has been excited and then relaxes back down. It tells us what is around that hydrogen. It tells us something about its environment. And we can use that information to then figure out what our molecule is. So we get an idea of what the molecule looks like and what it's around based on this energy that is released. So we are going to focus mainly on proton NMR because we're not going to have a ton of time. But there's proton NMR, and then there's a thing called carbon-13 NMR. So the proton NMR tells us where all the hydrogens are, like tells us their environment, and then the carbon NMR tells us the environment of all of our carbons. We're going to do the protons because proton NMRs are operationally much easier to do than carbon NMRs. A proton NMR takes maybe 5 minutes to set up the entire experiment and get data. The actual taking of the NMR, getting the spectra, only takes about a minute, where a carbon NMR takes anywhere in the neighborhood of 8 to like 12 hours. So proton NMR is what you will mainly use. So there are 5 basic pieces of information you get from a hydrogen NMR, right? The first is the number of signals, right? And the number of signals tells you how many unique hydrogens or groups of hydrogens there are in your molecule. So this is first pass. It's like we'll let you know how many different types of hydrogens there are, right? The second is the chemical shift. The chemical shift, that is where on the spectra, where on the scale these signals appear. And where these signals appear on that scale, their chemical shift, that tells you the environment that the hydrogen is in. What functional groups, what structures are around that hydrogen. Next, we have the integration of the signal. No math here, but this is kind of exactly the calculus definition of an integral, which is it is the area underneath the signal. And that area corresponds to how many hydrogens are making that signal, right? How many identical hydrogens there are that all make this same signal, right? Then there's the splitting of the signal, and the number of peaks that are contained within a signal tell you about how many hydrogens are next to the proton making that signal. So it tells you how many neighbors there are on adjacent atoms. And then there is the coupling constants, which this does involve math, but the coupling constants tell you that are the distance between the peaks in a signal. And what that tells you is that tells you the relative orientation or the angle between the hydrogen making the signal and the neighbor that is causing that signal to be split into multiple peaks. So the first thing we're going to talk about is we're going to talk about the number of signals. So the number of signals is kind of when the energy, each hydrogen or each type of or group of hydrogens, when they relax from the beta state to the alpha state, they give off energy. And in an ideal world, that energy is all going to be unique, right? But there's something called, there are hydrogens that are chemically equivalent, which means the NMR sees them as being the same, or they are in the exact same environment, right? So each set of chemically equivalent protons, so each set of hydrogens that are unique, give a signal in a spectrum. These signals, I've been calling them signals. Their technical name is resonances, but 6 of one, half dozen of another. You'll have to forgive me if I sometimes refer to them as peaks. I'm going to try not to, but that's just kind of like the common way of referring to them as, oh, how many peaks are in your NMR? Well, really, it should be how many resonances or how many signals, right? So the number of signals or number of resonance in the spectrum tells you how many chemically non-equivalent protons there are in the molecule. So if you look at a molecule, here, yeah, no, that's fine. So if you look at a molecule, let's say butane, right? You can look at it and you can say, well, there's these hydrogens here, these hydrogens here, these here, and these here, right? But this molecule is symmetrical. So, if you draw the molecule like this, you can see there's a plane of symmetry. So, in the NMR's eyes, right, the NMR doesn't see all of these protons, let's call them A, B, C, and D, because the molecule is symmetric. So it sees A and D as being exactly the same, and it sees B and C as being exactly the same. So in the NMR's eyes, the molecule looks like this, where you've got A and D here, and B and C here. And B in this carbon, the carbon that has hydrogens B and C on them, they're just connected to something. It doesn't know what, it just knows it's connected to something. So butane would have two peaks. Has two signals / resonances. Right? So when there's symmetry in the molecule gets simplified because the NMR only sees half the molecule because of symmetry, right? Another way that you get chemically equivalent protons, right, is we'll go back to our butane example here, is if you have hydrogens on the same carbon, so H's on the same carbon are the same to the NMR. So, right, we know if we were to draw this, we could say like, hey, we have this H, and then this red H, and then this green H, right? And we know they're not all exactly the same, but think about the NMR as taking a picture of all the hydrogens in their magnetic fields. So we learned early on that it is easy for, I'll do my little simplified R. It is easy for carbon-carbon single bonds to rotate, right? So as the NMR is taking this picture of the molecule, each time it takes a picture, one of those hydrogens move, right? So one picture, the black hydrogen goes from being in plane to on the wedge. The red hydrogen goes from being on the wedge to the dash, and the green hydrogen ends up in plane. And then the next picture, it rotates again. And now they're all in different places. So what ends up happening is the NMR just ends up averaging all of these different conformations, all these different conformations together. So it sees the hydrogens on the carbon, it sees the black hydrogen, the red hydrogen, and the green hydrogen as all being the same hydrogen. Because every time it takes a picture, it's just seeing magnetic field, right? Every time it scans, the magnetic field from the black hydrogen looks exactly the same as the magnetic field from the red hydrogen or the green hydrogen. And so the NMR can't tell them apart. So whenever you have a CH3, the NMR sees all three of those hydrogens as being the same. When you have a CH2, the NMR is going to see those hydrogens as being the same, barring shenanigans that happen with chiral centers. And we're not going to worry about shenanigans. No shenanigans, right? So we are going to just go and say, hey, when you have a CH2, right? So something like this, the NMR is going to see those two hydrogens as being the same. And then a CH3, the NMR sees these as being the same. But like we talked about a second ago, because of symmetry, the NMR actually sees these 1, 2, 3, 4 hydrogens as being the same. 1, 2, 3, 4. And these 3 hydrogens as being these 6, 3, and 3. Those as being the same because of symmetry. Right. So I've got a few example spectra, but let's do a couple like simple examples for us to kind of like work through and make sure we got this. All right. Okay, so if we look at pentane, right? This molecule has a plane of symmetry, right? We can cut this molecule in half through the third carbon, right? So in the NMR's eyes, this molecule kind of looks like this, right? You have carbon 1, 2, and 3, 1, 2, and 3, and then after 3, there's nothing, right? There's just like a stop. So the NMR is going to say, hey, these hydrogens here on carbon 1 and these hydrogens over here, those are exactly the same. I'm going to just see basically this set of three hydrogens here that is green, but I see 2 of them, right? These blue hydrogens here on carbon 2 are the same as these hydrogens over here. So I'm going to see 2 sets of these hydrogens as well. And now my the hydrogen where the plane of symmetry is, carbon 3, there's no other hydrogens like them. So this molecule, so the NMR just sees this set of CH2s, and the hydrogens on carbon 3 are different than the hydrogens on carbon 2, and different than the hydrogens on carbon 1, right? So carbon 3, you might be saying, well, it's a CH2 here, and there's a CH2 on carbon 2. But the 2 hydrogens on carbon 3, right, what are they beside? What is their environment? Well, these right here, right, the ones on carbon 3, they're beside a CH2, and then they're beside, effectively, in the NMR's mind, nothing, right? This R effectively is nothing as far as the NMR is concerned. While the hydrogens on carbon 2, one, the NMR sees 2 sets of them, right? It sees 4 hydrogens there, where on carbon 3 it just sees 2. And the hydrogens on carbon 2, they're beside a carbon that has 3 hydrogens on it, and a carbon that has 2 hydrogens on it. So carbon 2 has different stuff around it. The hydrogens on carbon 2 have different stuff around them than the hydrogens on carbon 3. So even though they're both CH2s, they're different CH2s, right? They're not in 100% exactly the same environment. So the NMR sees them as being ever so slightly different. If we look at like an aromatic ring, like we have over here next, now what tricks people is there is a plane of symmetry, right? So remember that single bonds can rotate. So this is going to rotate around. And as far as the NMR is concerned, right, this kind of ends up averaging out. And this molecule, kind of like meso compounds, if you could draw one isomer that is symmetrical, then we consider all the isomers or all the conformations to be symmetrical. So even though like you think like, oh, this is on the right and this is on the left, right? As you rotate around the single bond, there comes a point where you get a conformation that has a plane of symmetry down it. So the NMR sees that compound as having a plane of symmetry, because it does. So when we look at this, how many unique types of hydrogens, how many hydrogens that are not like anything else in the molecule do we have? Well, this CH3 here, these 3 hydrogens, right? They're not like any other hydrogens in the molecule. The thing that they're closest to is they're closest to these 3 hydrogens. But this carbon that has these hydrogens on it, I should probably use a different color. Boop, we'll use a different color here. These hydrogens here, right? The blue ones are on a carbon that is bonded directly to the aromatic ring, and the green ones are on a carbon that's bonded to an oxygen. So the blue hydrogens and the green hydrogens are in different environments, so they're going to give different signals because they're not in the exact same environment. So we can say, hey, the blue hydrogens are one set of hydrogens. Here's one type. I don't know where the R came from. And then we've got these green hydrogens. That's a second type. That's type 2. And this is a different type, right? Now, I've got a hydrogen here and a hydrogen here. Now, the molecule is symmetrical, which we showed down here. So that means this red hydrogen is exactly the same as the hydrogen across from it. And then the gray hydrogen is exactly the same as the hydrogen across from it. But are the red hydrogen and the gray hydrogen the same? No, because the red hydrogen is on a carbon that's beside a carbon that is bonded to a methyl group or another carbon, while the gray hydrogen is on a carbon that's bonded to a carbon that's got an oxygen on it. So the red hydrogen and the gray hydrogen are different because they are not, again, in the exact same environment. So the environment changes as you walk down the chain. So if you have, so the red hydrogen is not, even though they're both on carbons on aromatic rings, the red hydrogen and the gray hydrogen are seen as being different. So this is one type, this is another type. So there are 4 types of hydrogens. So there are 4 types of hydrogens, and so that equals 4 different signals. Let's do another example here. So we look at this. How many types of hydrogens are there? How many unique hydrogens are there? Well, let's draw in some hydrogens. We'll have blue, green, and red, and we'll do gray, right? So the blue, the green, and the red, they are all CH2s, but the blue hydrogens are closer to the OH than the green or the red. So the blue hydrogens, that is one type, right? The green hydrogens are closer to the OH than the red hydrogens, or you can think about it as the green hydrogens are beside a CH2 and a CH2, while the red hydrogens are beside a CH2 and a CH3. So they're not in the same environment. So this is going to be a type here. The red ones are going to be a type. And then the gray hydrogens are going to be a type. And finally, the OH, this hydrogen here, is an extra type. So we've got 1, 2, 3, 4, 5 types of H's. And that's going to equal 5 signals in my NMR. So when I look at my NMR, I should have 5 signals if I had this molecule. So let's say I have this now. Label all of our hydrogens here. I'm kind of giving it away by labeling them the same. So the gray hydrogens are unique, right? They're a CH3 beside a ketone. So this is one type. The blue hydrogens, they're the only CH2 in the molecule. There's no other CH2s. So that is also one type. The orange hydrogen, again, is unique. There's only one CH in the whole molecule, so it has to be its own type. And now these two methyl groups on this isopropyl, these are the same. This is one type. So just like, well, I can do this. So just like a CH2, right? Having two having two hydrogens on the same carbon makes those hydrogens the same. Having two identical carbon groups on the same carbon makes those two carbon groups the same. So these two methyl groups are seen by the NMR as being the same. And it's for the same reason as we had back here, right? So it's the same reason here, where these hydrogens are switching places really fast, and so the NMR sees them all as being the same. So when you have two carbons that are that are sharing a carbon, the NMR basically just sees these three green hydrogens as the same, and these three green hydrogens as the same, and these three green hydrogens as the same group of three hydrogens. And then as you rotate around the bond and you switch places, the NMR just sees those things being exactly the same. It just keeps seeing them over and over again. So if you have a carbon that has two identical carbon groups sharing a carbon, they're going to be the same. So if we look at this, we have the gray one. So counting's hard. 1, 2, 3, 4. There are 4 types of H's. All right. So another example of this is, let's say we have something like this, right? This CH3 is here. Then we're going to have this H here. Then we're going to have 2 hydrogens here and a CH3 here. I'm going to be a little bit quicker. CH3 and an H. This blue carbon right here has 2 ethyl groups on it. So the NMR is going to see this ethyl group and this ethyl group as being exactly the same. You could also think about it as there's a plane of symmetry, right? If we drew the molecule out kind of like this, where you can basically, the screen cuts the molecule in half, where all of this is in one plane, and that is in the plane of the screen. All of that is in the plane of the screen. And then there's an ethyl group forward and an ethyl group back, and so that gets cut in half. So as far as the NMR is concerned, these two CH3s are one type. These two CH2s are one type. Then you have your H here is one type. And then you have your CH3 here is one type. And there are no H's there, right? There's a C double bond O. There's an ester there. There's no H's. So you're not going to know anything about this carbon right here because there's no H's on it. So we should have 1, 2, 3, 4 types of H's. And you should have 4 signals. How many types of H's does this have? Well, all of these CH2s are the same, right? Right, I could, if I rotate it, right, if I didn't have the dot there, you wouldn't be able to tell that I had rotated the molecule, right? So all of these hydrogens are the same. So there's only one type here. Now, if I put a substituent on here, right, now there's a plane of symmetry down here. So this H here is unique. These two H's here are unique. And then these two H's here are unique. So, and then each of these CH3s, because they're sharing a carbon, all look the same to the NMR. So I have the gray hydrogens are one type, the blue hydrogen is one type, red is one type, and then green is one type. All of these have been 4 for some reason. So I have 1, 2, 3, 4 types of hydrogens. And that's going to equal 4 signals. All right. So I have a couple actual spectra. So if we look at methyl pivalate, which I have the structure up in that corner, it has a methyl ester, it has a CH3, and then it has 3 CH3s on this terbutyl group that all look the same. So you've got the methyl hydrogens of the ester, which is one type, and then you have the 3 hydrogens, or the 3 CH3s of the terbutyl group, which all look like one. So there should be 2 types of hydrogens here. So there should be 2 signals in the NMR. Similarly, 3-pentanone, right? This molecule has a plane of symmetry. We can cut it in half, write down the ketone. And so that gives you a CH3 and a CH2 on each side of the ketone. So the methyl groups at the end of the chain, the NMR sees those as the same and as one type. And the CH2s, the NMR sees as being the same in one type. So there are 2 types of protons here. So there should be 2 signals in your NMR. Here I have ethyl acetate, and there are 3 signals in the NMR. And that means there are 3 types of protons. There's the CH3 beside the C double bond O. And then there's the CH2 that's bonded to the oxygen of the ester. And then the CH3 at the end of the chain. So there again, we have 3 types of protons. So being able to look at a molecule and know how many signals you are going to have is kind of the first step of being able to know if you've made the correct compound or not. Because if you have that, you kind of be like, oh, okay, my molecule should have 6 types of hydrogens. And then you look at your NMR and you see 6 signals. You can be like, okay, that's pretty promising that the types of hydrogens match. Then you can get further into analyzing the NMR to make sure you have the right stuff. The next thing that you kind of look at is you look at the chemical shift. So this is where on the spectra does your signal fall. And where your signal falls is based on how much of the magnetic field from the NMR, or how much magnetic field in total does the hydrogen nuclei feel. So where that signal falls, it's called the chemical shift. And the chemical shift of a given signal is determined by the environment that the proton is in, right? So a proton that is by If we look at methylpivylate again, the proton on the hydrogens of the carbon that are on the oxygen of the ester, those hydrogens are in a different environment and show up around 4, while the hydrogens on the tert-butyl group aren't directly bonded to a functional group, so they come much closer to 1, right? So that's called the chemical shift. So changing the magnetic field that the hydrogen feels changes the difference between the energies of the alpha and the beta state. And so that difference in energies corresponds to where the resonance or the signal will show up in the NMR. So the scale that we have is called the delta scale, and it runs from 0 to 12 ppms. And so ppms is parts per million. And basically the ppm is a ratio used to standardize measurements. And basically there's some math that it does, because if you didn't use ppm, every NMR that had a different frequency would put the signals in a different place on the scale. So using ppm allows us to standardize everything, that no matter what type of NMR you use, if a signal is supposed to come at 3, every NMR will have it come at 3. Whereas if you used a 300 megahertz NMR and a 500 megahertz NMR, the different frequencies of NMR would put that peak in a different place. The ppm basically takes the frequency of the NMR out and just gives us ppms. So the scale runs from 0 to 10. The vast majority of organic compounds fall between 0 and 10. The only time you get 12 or near 12 is when you have a, what's it called? When you have a carboxylic acid. So there are some terms that we use. We can say that protons are shielded. So shielded protons do not feel as much of the magnetic field as they should. So basically, if a proton's shielded, it is protected from the magnetic field and feels less field from the NMR. And basically, electrons shield protons. So the more electron density you have around a proton, the more shielded it is. Protons can also then be de-shielded, where they have fewer electrons around them and they feel more of the magnetic field from the NMR. So you either are protected from the field by your electrons, or you're exposed to the field because you don't have very many electrons around you. So practically what this means is that shielded protons, or more shielded protons, are further to the right on the spectrum. They're more upfield. Counterintuitively, this means they have smaller numbers. You get smaller ppm values when you're upfield. De-shielded protons are on the left side of the spectrum. They are more downfield, and being downfield means bigger numbers. So I've got a little thing for you here, right? So you can see here on this slide, right? De-shielded downfield is closer towards 10 or 11. Upfield is closer towards 0. Now, what happens when you run an NMR is we have to run the NMR, I should have said this earlier, we have to run the NMR in deuterated solvent. So the NMR sees protons because of their spin. Deuterium, because it has an extra nuclei, sorry, not an extra nuclei, an extra neutron, has a different spin. Its nucleus has a different spin than a hydrogen's nucleus. So the NMR does not see the signal from a deuterium. So we use solvents like CdCl3 to dissolve our samples, and that chloroform has very little hydrogens in it because we replaced the hydrogens with deuterium. So if we didn't use deuterated solvents, we would just see a great big peak for our solvent and then see none of the peaks or none of the resonances from our compound of interest. And so what happens is we will use the little bit of regular undeuteurated chloroform, so CHCl3, as an internal standard to basically calibrate our spectra to what it should be. So um, you could say like, hey, I ran my NMR, I got this value, and this chemical shift is relative to my chloroform, my residual chloroform signal being set to a given value. Um, Sometimes you will use TMS, tetramethylsilane, as an internal standard, and tetramethylsilane shows up at 0. Its resonance is at 0. So you can say, hey, I got this chemical shift. I got a chemical shift of 3, and that for this signal, and that is relative to TMS being at 0. So someone else can run an NMR across the world and get the exact same thing you did. So knowing that exact value, that exact chemical shift is really important for determining the structure of your compound. And there is a whole table of values that you should probably be familiar with. Yes, you need to know these. I know we only have a day or a couple days to go over this. So really, the ones that really matter, right, is we can kind of clump all of the alkanes. So CH3, CH2, and CH. Basically, these are all effectively the same thing, right? Anything from 0.8 to 1.7 is just hydrogens on carbons that aren't near functional groups, right? And then ethers being between 3.2 and like 3.8 for the most part. That's really important to know. So this CH3 on the oxygen here of an ether, and then the CH3 on an ester being from like 3.8 to 4.5, that's really important in diagnostic. The aromatic hydrogens being from like 6.5 to 8 is important. And this changes based on what's on the aromatic ring. And then aldehydes are really diagnostic. They come in this really narrow range of 9.7 to 10. So I would suggest it probably be in your best interest to at least know the alkanes, ethers and esters, aromatics, and aldehydes to just have like a rough sense of those so that if you look at a spectra, you can kind of predict what you're going to have. So you can look at methylpivylate. So these 9 hydrogens here, the 3 CH threes on the tert-butyl group, right? They're not by any functional groups, right? So the 3 methyl groups are bonded to a carbon that doesn't have a functional group bonded to it. So they're going to be boring and they're going to come somewhere around 1. A little over, a little under, but you would expect them to come somewhere around 1. And then the methyl group on the oxygen of the ester is going to come up here around 3.8. It's going to be much higher. If you look at the 3-pentanone, again, the CH3s at the end of the chain, they're boring. They're not by any functional groups. They're not bonded to a carbon that's got a functional group on it, so they're going to be around 1. But now the CH2s that are beside the ketone, they're bonded to a carbon that has a functional group on them. They're going to be at like 2.5. And we can come over here and see CH3 beside a C double bond O between 2 and 2.7, right? Ethyl acetate, you kind of see them both put together, where you have the methyl group beside the C double bond O, comes here right around 2. The carbon, the hydrogens on the carbon bonded to the oxygen comes at around 4. And then again, the CH3 at the end is pretty far from a functional group, so they're a little bit above 1. So unless your carbon has a functional group bonded right to it, you're typically not going to see a change or much of a change from that functional group. And then here's an aromatic ring. We've got this methyl group that's on the oxygen of the ether. It's up here around just under 4. We have this methyl group that's on the aromatic ring. It's just above 2, and that's because it's beside the aromatic ring. The OH is here around 5. They move around. And then the hydrogens on the aromatic ring, they're up here over 6. They're a little bit lower than that 6.5 mark I gave you, but they're over 6. They're much higher than anything else.
So aromatic rings are special. The fact that the electrons and the pi bonds will move in a circle, we'll talk about this in organic too, but they move in a circle. So similar to how like the junior high physics experiment of like wrapping wire around a nail and putting a current through it, and that makes a magnet. That magnet's formed because the current is going in a circle. So these electrons moving in a circle around the aromatic ring, that causes a current that then makes a magnetic field. And that magnetic field is called magnetic anisotropy. And what happens is that field is formed so that it lines up with the magnetic field of the NMR. So it loops around the ring, and as it goes from from one side of the ring kind of around to the other, when it is by the hydrogen on the ring, it's pointing in the same direction as the magnetic field of the NMR. So the hydrogen just doesn't see the magnetic field of the NMR. It sees the magnetic field of the NMR plus the induced magnetic field from the aromatic ring. So it sees the field from the aromatic ring as well. So it effectively sees more magnetic field. So it acts like it is more de-shielded than it would otherwise be. So it is, up around 6, 7, 8, as opposed to being at like 2. So I know, especially here at the end, there was a whole lot of information. What I think you should take away from the chemical shift stuff is where you come on the scale between 0 and 12 is really important. And there are some like easy ish to remember values that can help you kind of assign structures or assign parts of molecules. So knowing that between 0.8 and 1.7 is just hydrogens on carbons that don't have functional groups on them. Up around 3.5 ish to like 3.8 is where an ether comes. 3.8 to like 4.5 or 4.2 is where the hydrogens on a carbon that's bonded to the oxygen of an ester falls is important. That's 6.5 to 8 for aromatics. And then the hydrogen of an aldehyde between like 9.7 and 10. Those, if like I could get you to put like that handful in your head, that would be super useful and would help you kind of know anything that you need to figure out. So be able to assign the types of hydrogens or how many types of hydrogens there are in a molecule, so you know how many hydrogens you should expect or how many signals you should expect in your spectra, and then know those like 5 chemical shifts so that you can start to assign structures from a spectra. So we'll kind of work through the other information that you get from a proton NMR next class.